Swayam Prabha. Digital India. Educated India.
So let's work out an example here. So here we have, like we said, the inputs are an activity. So we have here activity A to H, given you the predecessor relationship here, the optimistic duration in days, the most likely duration, the pessimistic duration. Okay, now this is your basic input information, and what is asked from this. So what are the questions we can ask when we are given this? One is we can look for the most likely project duration. Okay, so that is one of the results we'll have to get. We can certainly get what the critical path is. Okay, now here are some interesting questions which PERT will give you. We should be able to ask, what is the probability that the project duration is greater than or equal to 95 days? Okay, we could not ask such a question in CPM. Or what is the probability that the project duration is less than or equal to 85 days? Okay, or what is the probability that the project duration lies between 85 and 95 days? Okay, or given that my probability is 90%, okay, 90%, what is my confidence of finishing my project at a 90% probability? What is the duration I should finish my project at 90% probability? So all of these types of questions can be asked from your basic PERT data. Now what we have gone down here and done is we have actually put up the network. Okay, so this is the same network, the activity predecessor relationship is used to put the network, and we go on to the next step in PERT, which is to calculate the expected value. So here you can see I have used this formula, okay, to calculate the values in this column, and you will be able to associate it. So if I take for example 15.7 here, A is 10, okay, plus 4 into 16 plus 20 divided by 6 gives me 15.7, which is the expected value. Similarly, I have given you worked it out for E here, that is 25 plus 4 into 30 plus 32 gives you 29.5. So you have calculated similarly for all the other activities, calculate expected duration, and then we move on to calculating the standard deviation for the activities. So here we apply this formula, and what we get here again is for the activity A, we have basically said B minus A, which is 20 minus 10, okay, divided by 6. So this gives me, it's a rounded off value of the standard deviation of the activities, and from the standard deviation we square it to get the variance values for each of the activities. So with this, the table of, we have taken the basic input data, converted it to expected duration, the standard deviation, and finally the variance of the activities. Now in the next step, what we do is we like we discussed in the stepwise procedure, we take the expected values. So for example, A is 15.7 here, okay, for B 11.2 comes there, for C 6.8 comes there, for D it's 18. Okay, we have just used the expected values as the basic duration of the activity, and we have done the forward pass and the backward pass. So you will get the early start, the early finish, okay, for all of the activities. You can see the early start, early finish, and some of these values are rounded, okay, rounded off. So you might not you'll see based on what, it's not exactly what is, it's a rounded off value which I have here, okay, and when you add the activities, so if I look at this, you can take a guess at what the critical path is. You should be able to do that, but ultimately we land up with a project duration of H finishes on 89, and that's the project duration. We are saying 89 days is the project duration, but like we discussed, it's not just the project duration, it happens to be the mean of the project duration. Okay, it happens to be the mean of the normal distribution showing the project duration. Now we do more computations. Okay, so for example, we can find the critical path. So you can see the critical path goes through A, B, E, G, H. Okay, and now, like we discussed earlier, I will have to find the variance of this 89 being the mean. What is the variance of this distribution? We remember it is the sum of the variances. So I have to take the sum of the variance of A, B, E, G, H, okay, and sum it up, and I get a total variance of 10.44. Okay, so that is the variance along this path, and I take the square root of that to get the standard deviation as 3.2. So my project duration now is defined as a normal distribution with a mean of 89 and the standard deviation of 3.2. So this has characterized my project duration, the distribution, by giving the mean and its standard deviation. So now we go further. So this has given me, so this is really the core of PERT. Okay, all of the assumptions we have used, everything has now been applied, and we have now, to be able to use this data to answer questions, we are basically using basic probability and statistics approaches, okay, which is to read the values of a normal curve. But up to here is where PERT's contribution has been. Now you have to, like we discussed in the initial part of this lecture, be familiar how to read a normal distribution values, the z values. So here you have I've given you the curve in the table in two parts. One part you can see the distribution here, and it gives you the area for this level of area. So here, given a certain distance of z from the mean, what is the area under the curve is described here. Here it gives you shows the shaded area and discusses what the shaded area is based on the distance again from the mean. Okay, now you should be familiar with how to interpret these two, and we will be using these curves for further analysis. So remember, the first one of the other questions we asked from a probabilistic perspective, what is the probability that the project duration is more than 95 days, or it's greater than or equal to 95 days. So if we take, so remember, so this is back to our normal distribution of project duration. We had a mean of 89, we had a standard deviation of 3.2, and we are now looked at the standard deviation here. So we have one first standard deviation, second, third, and we have now the values here are the days to which for the corresponding standard deviation. Okay, so these are the project duration days. So when we say that that project duration of 95 days, it falls somewhere here. So to find the probability of that, basically what we are saying is what is the area of this shaded part of the curve. So my 95 days is here, and for the project duration to be greater than 95, it has to fall in this area. So what is the area of this part of the curve? So we go to the tables. Okay, as you know, you have to go to the tables, but to go to the table we really have to first find what the z value here is. So the z is actually the number of standard deviations from the mean. So here we have 95 as the mean. So we are basically 95 as the value, we have 89 as the mean. I am basically using this formula which says it's a value minus mean divided by sigma is the z value 1.88. Okay, and what we do with, so this 1.88 is right here, that is a distance from the mean. It's 1.88 standard deviations from the distance from the mean. That's where 95 days is in this normal curve, and I actually go to the normal table and look at 1.88. So here we have the table 1.88, okay, 1.88, and I get the value 0.9699, okay, which is, now you can see 0.9699 represents this whole area. So the area I want is the area beyond that, which will be 1 minus 0.9699. So, the probability of project duration being greater than or equal to 95 is 0.0301. Okay, so I hope you followed how that computation was done to be able to get this value, but basically what we are doing is transforming the 95 into the number of standard deviations away from the mean and using that to go to the normal distribution table to find the probability value. Okay. Now, we had another question, which was what is the probability that the project duration is less than or equal to 85 days. So, it is the same process we follow, but remember now the shaded area we want is this, that is the probability we are looking for is that the probability that the project duration is less than 85 days, less than or equal to 85 days. So, when we go with this, we are again applying the same formula here, that is we are looking at 85 minus 89, so because the value of x is 85, the value of the mean is 89 divided by the standard deviation. So, this is at minus 1.25 standard deviations away from the mean. Okay, so, that is the value of x from the mean, and now I go to the normal table with this portion shaded, and you can see I am looking at minus 1.25 and I get 0.1056. So, 0.1056 is the shaded area. Okay, so, I can read this directly off. Okay, so, the probability of the project duration being less than or equal to 85 is 0.1056. Okay, so, this is again very similar to the earlier question. It is just that the area shaded is different, and I will have to use the appropriate distribution curve to read it directly off. I could use the other normal distribution table also, but I will have to do a little few more operations to get to this number. Okay, so, we can use both tables, or you can use one of the tables, but you should be familiar as to how to use it effectively. Now, we go to the third probability question, which was what is the probability that the project duration lies between 85 and 95. Okay, so, the shaded area here is again what is represented by this relation. So, we want the probability to lie between, it should be greater than or equal to 85 and less than or equal to 95, and this shaded area we can calculate it from our earlier values. Okay, we had, remember, this was, we got this as the area here was 0.0301, the area here was 0.1056, and now we know the area under the whole curve is 1. So, if we subtract 1 from subtract from 1 these two areas, we will get the resulting area which is shaded here, which is 0.8643. So, we are saying the probability of the project duration lying between these two values is 0.8643. So, you can see that we have started answering probabilistic based questions based from a project perspective. Now, we come to a different question. Okay, so, here I am giving you a probability. I am saying that I want to know within what duration my project can be completed, and I want a 90% certainty that it will be completed in that duration. So, how do we do this? So, basically if we go back to the normal curve, we can see that what we want is the shaded area is here, it shows 90% of the area shaded, and what we want to know is find the duration for which this 90% of this area would be covered. So, we have to work it the other way. Okay, so, if we actually take, for example, the typical normal distribution with percentages of areas given. So, you can see the first so we have divided this into 1, 2, 3 standard deviations and 3 standard deviations, and this end first 2% of the area, and this area is 14%, this area is 34%. So, as you accumulate, you get 2, 16, 50, you can see 84, and when I am saying 90, 90, it should be less than or equal to 90, we are looking at close, it should be when we say we want a 90% certainty, we are looking at somewhere between 84 and 98, which is what we saw between the first between 1 and second standard deviation, and that is what we are kind of highlighted here. So, we are now trying to find the value at of the how many standard deviations. First we have to find is this point from the mean, and then convert those standard deviations into a duration. So, the first step here is to be able to see where we are as far as the number of standard deviations we have from it. So, we look at, we go for the 90% or 0.90. So, I do not have a 0.90 exactly, but I have a 0.9015 and a 0.8997. So, obviously 0.90 will lie between these two values, and what I have to do is do an interpolation. So, here we find, so this is the equivalent of between 1.28 and 1.29 lies my 0.90 value. So, we just do an interpolation. You can see the basic interpolation formulation here, which is your typical interpolation formulation, which you can do, and you will find that when we kind of solve this, value is so many standard deviations from the mean. Now, what we need to do is convert that into a duration, which we have to be able to say. So, the duration basically is 89 plus so many standard deviations multiplied by the standard deviation, and we get 92.87 days as the duration at which I have a 90% chance of finishing the project within. Okay. So, given that if I am 90% confident that I will finish the project within 92.87 days. So, this has given an illustration as to how both the normal distribution of project duration can be used both not only to estimate the duration given a particular probability, but also the probability given a particular duration. So, if we look at a summary of the results from the examples, okay, you can see that we took the basic information, okay, we added the expected value, the mean, the standard deviation, the variance. We use the expected value here to calculate the expected project duration. That became the mean for our normal distribution. Okay, we found the variance of the normal distribution, then converted that to the standard deviation through the characterizing the normal distribution. We were able to get all of these values which we solved step by step. Okay, now in addition to this, floats, just as we did in CPM, floats and other things can also be calculated, but we are not getting into that in this session. So, now I hope this has given a broad perspective on how you can do PERT calculations, and it's fairly involved, but the interesting questions we can ask from doing PERT certainly add a lot of insights into how the project is going to go, and we will be able to map the uncertainties and all the other issues with it. Now, we had looked at probabilistic scheduling. Right now we went into detail from the expert opinion and PERT perspective, but do realize that data driven perspective is also very important, and it can really add a lot of value to a project where the data exists. And between simulation and PERT was very popular. It's really a very good methodical technique, but with computing power increasing, more and more people are shifting to simulation based techniques. One of the key reasons for that is PERT has several assumptions, and we saw several of these assumptions, and these assumptions certainly limit the value of the results from PERT. Okay, but while the value and the results are limited, there is a lot of value still in PERT to be able to get the experts together, get the team together to quantify the risks, to articulate what the risks actually are. There is a lot of benefit in that. And as we have seen, PERT can be used to generate several interesting results, and as we go forward, I think the introduction to PERT is really useful, because it teaches you to think in terms of probability, thinks in terms of project duration or project events and the probability that is associated with it. Okay, in CPM we never had a chance to do that. So, here it becomes an introduction to probabilistic thinking for projects, which is very, very important in managing projects. Okay, if you have questions and discussions, please post them online. and we will take it up as you post it. Thank you.